Okay, welcome back. And here you're looking at a power spectrum. And a power spectrum is different from the graph or figure we've seen of vibrations so far, because the figures we've seen so far have shown time across the bottom, and then intensity, kind of rising and falling up the y-axis. This graph is showing us amplitude, the same strength on the y-axis, but different frequencies across the bottom. Right? There's no measurement of time in a power spectrum. So this is showing us a complex wave, a complex vibration made up of two components, two parts, a 100 hertz and 200 hertz component in a complex vibration. Okay? Now, let's see, whoops. Hold on, my computer is not set. There we go. Now, we call the relationship between these vibrations harmonics. Right? So the first harmonic is the lowest frequency. The H1 is the first harmonic. The second harmonic is always exactly 2 times the first harmonic. So if the first harmonic is 100 hertz, the second harmonic will be 200 hertz. If the first harmonic is 200 hertz, the second harmonic will be 400 hertz. See? If the first harmonic is 300 hertz, the second harmonic will be 600 hertz. Or going lower, if the first harmonic is 40 hertz, the second harmonic will be 80 hertz. And there are third and fourth and fifth harmonics, and each of those will be even multiplications of the first harmonic. So if I have a 60 hertz H1, well then 60, H2 will be 120, H3 will be 180, 240, etc. Okay? So this lowest harmonic is what we call the fundamental frequency, and we mark it as F0. Excuse me. Now, returning to our familiar vibration that repeats itself every 10 milliseconds, which of course is a 100 hertz vibration. And then we've seen this one before, a 5 millisecond vibration, which repeats itself 200 times every second, so a 200 hertz vibration. And together they create this complex vibration, which is actually the vibration in the air that you hear, right? It's not that there are two sounds combined together. There's one complex sound. But to measure it, to describe it, it has the properties that are the same as a vibration created from those two basic sounds. So that's why we call that complex vibration a 100 hertz plus 200 hertz complex vibration. Okay. Now, I'm going to draw the spectrum of these complex vibrations. So let's look at one that's a little more complex. I think I showed this last week. And you'll notice that the vibration repeats itself, 2, 3. And if you look closely, so instead of being kind of even, it kind of goes high early, and then it has this ripple, and then it goes up, and then it ripples down. Okay? So it's not the same kind of vibration we've seen so far, but it's a complex vibration that has the properties equal to a combination of simple vibrations. And in this particular case, it would be the combination of a 100 hertz, 200 hertz, 300 hertz, and 400 hertz components. You'll also notice that the amplitude, the strength of each of those components is not the same. The 100 hertz wave or vibration is stronger than the 200 hertz vibration, which is stronger than the 300 hertz component or vibration, which is stronger than the 400 hertz, right? Now, to see the power spectrum, which means to ignore time, right? So time goes across the bottom. So I want to look at frequency. So here are the different frequencies: 100 hertz, 200 hertz, 300 hertz. So really what I want to do is I want to kind of come in here and look at the data, look at the measurements from this side, right? And I'm going to see frequency across the bottom and amplitude across the top. And it's going to look like this, right? So here I'm looking down those vibrations, ignoring the change over time, and just looking at the differences in intensity, the differences in strength between the four components. I'm also measuring the frequencies at which those harmonics occur. Okay. Going back, right? Harmonics, right? So the first harmonic was 100 hertz. Therefore, the second harmonics is 200 hertz, 300 hertz, and 400 hertz. Okay. Now, go back a second. So if we're looking down, what we're really focusing on are here, just this front edge, right? So these are the lines that we're seeing in the power spectrum, right? So let me turn back. Hopefully you get the mental image of what we're looking at. Okay. Those are a complex wave made up of four components, four harmonics, at 100, 200, 300, and 400 hertz, each with slightly lower intensity. Okay. So let's get a little bit of practice. Here I have a complex vibration, and I want you to decide to draw the power spectrum. Okay. Well, I'll tell you the components. Right? It's made up of simple waves. So it's a complex wave that takes 20 milliseconds to repeat itself. Right? Therefore, it repeats itself 5 times in 100 milliseconds, or 50 times every second. And it's made up, so it's 50 hertz, right? So, and it's made up of two components, a 50 hertz component and a 100 hertz component, right? So my question to you is, what will the power spectrum look like? So pause the video and draw on a piece of paper the amplitude and the frequencies, and then add the lines where they are supposed to be. Go ahead, pause. I'll wait. Okay, thank you. Are you ready? Let's take a look. Did you get, right, I was going to point out that the amplitude of the 50 hertz component and the amplitude of the 100 hertz component are approximately equal. Right? So in the power spectrum, you should draw them the same height. And it's a principle of the vibration that the intensity above the line and the intensity below the line are approximately equal. Okay. And therefore the power spectrum should look like this. Right? There's one component at 50 hertz and one component at 100 hertz. Okay. Frequency across the bottom, or this way I guess, frequency across the bottom, amplitude up the left side. Let's try one more. Oops, just a moment. I've clicked the wrong button. Okay. So here's a different complex vibration. Okay. It repeats itself every 10 milliseconds. So its fundamental frequency is probably 100 hertz. Right? But what's the frequency spectrum look like? Well, to create this complex vibration, it's a combination of a 200 hertz vibration at the top. Right? We've seen a 5 millisecond vibration repeats itself 200 times every second. So that's 200 hertz. And then the B example we've seen before, the vibration repeats itself 3 times every 10 milliseconds. Oh, we haven't seen this one before, have we? No. It repeats itself 3 times every 10 milliseconds. Therefore, it repeats itself 30 times every 100 milliseconds, or 300 times every second. So it's a 300 hertz vibration. So the complex vibration we're interested at the bottom is a complex vibration with a fundamental frequency of 100 hertz made up of 200 hertz and 300 hertz components. Okay. So what's the power spectrum look like? The power spectrum should look like this. There's a component at 200 hertz. There's a component at 300 hertz. Right? We just saw the two basic sounds. But what's the F0? Well, the F0 can't be 200 hertz because if the first harmonic is 200 hertz, the second harmonic is 400 hertz because 200 times 2 is 400. And the third harmonic would be 600 hertz. But here I have a harmonic at 200 hertz and a harmonic at 300 hertz. And the only way that's possible is that if there's a lower harmonic that isn't actually part of the components. Right? The actual fundamental frequency is 100 hertz, even though it's made up of simple vibrations that are higher than that, which actually is consistent with or matches what we saw before. Right? There's a harmonic that is actually not part of the vibration. Right? It's actually, remember this, right? It's this complex vibration that is 10 milliseconds or 100 hertz for the complex wave, even though neither of the components is 100 hertz. Okay, we'll stop there and then we'll take a short break, and I'll see you in the next video.